right. How's it going? Everybody happy to be here? Ready to do?
I have a question.
What? I'm always happy to be here. What's up?
I get confused with this problem.
What's the
I've done
problem?
it like 3 times.
Which one is it?
It's right here. Like I always get confused with the wording. I don't know.
Okay, let's take a look at it. I'll bring it up on here. This one right here? Okay, so there was a homework question. This one comes out of the section 10.1. And it has a couple parts. So this is getting at sort of the overall picture of hypothesis testing. So a can's labeled 15 ounces, and the quality control manager, they want to make sure that they're not overfilling or underfilling their cans, right? Because if you're overfilling it, what's the problem? As you're losing money, right? Because you're putting more in there than you need to. If you're underfilling it, what's the problem? Well, maybe that's the problem. What's the bigger problem if you're underfilling your cans, probably though?
Customers?
Yeah, is that you're lying to your customers about what they're getting. But yeah, so you don't want to overfill because you lose money. You don't want to underfill because then you're falsely advertising the size. So hopefully the mean, so we're talking about a mean here, an average, is equal to 15. Right? That's what you're hoping. It's possible what? What should be our alternative here? The not equal. Yeah, it should be a not equal alternative because we're interested in seeing it either overfilled or underfilled. We're not just interested in one way or the other. So we would do a not equal to alternative. Okay. They obtain a sample of 76 cans. They measure the contents. The sample evidence leads the manager to reject the null hypothesis. What is the conclusion? So if they reject, what is the null hypothesis? Is the null hypothesis that the machine is working or not working?
Not working. Working. It is like working.
Yeah, so what's the machine supposed to be doing? Filling the cans to 15 ounces. The null hypothesis is what? The null hypothesis is what? Null hypothesis is that it is 15 ounces, right? So the null hypothesis is our machine is working, right? Basically. The alternative is that it's not. So then if they reject the null hypothesis, is there evidence that the machine is out of calibration? They reject the null hypothesis. Yes. So the null is that it's working. We rejected it. So we're saying there is evidence it's out of calibration. So there is sufficient evidence to conclude that the machine's out of calibration. Okay. Suppose in fact it's not out of calibration. Did we commit a type 1 or a type 2 error? So we rejected the null when it was actually true. What type of error is that? That is a type 1 error. If you reject when you shouldn't, that's type 1. Right? So since we rejected the null hypothesis when in fact it was working, that is a type 1 error. Okay? So it led the quality manager to reject the null hypothesis when the null hypothesis is actually true. Yeah. That's type 1. Okay? And then the last one says, they informed the quality control department it does not want to shut down the filling machine unless the evidence is overwhelming that the machine is out of calibration. In other words, they're saying they really don't want to have to stop production and fix their machine. What level of significance would you recommend and why?
0.1.
So we have to decide which type of error is worse. So what do they really not want to do? Yeah. They don't want to stop their machines, right? So they're saying, I really don't want to stop the machines unless I really, really have to. In other words, they really don't want to reject the null hypothesis unless they really have to. Because the null hypothesis is everything's working, right? They really don't want to have to reject that unless there's strong evidence. So what they really don't want to do is commit a type 1 error. So they're saying, I really don't want to commit a type 1 error, so let's pick a low level of alpha. So we pick maybe a 1% alpha level, because this makes the probability of a type 1 error small. Okay.
There was another one, like in chapter 9, that I only gave you one try.
Yeah, there is a couple at the end where you only get one attempt at it. Yeah. That's just the way it was formatted, so I can't really change that.
Okay, can we go to it? 'Cause I don't know how to
Do you know what number it was?
do it. Give me 1 second.
Get out of here. Yeah. Any other questions while she looks for that?
36, the first one.
Homework 9. The first one? The very, very first one?
Yeah.
Right here? Down at the end?
the last.
Yeah, there was a couple like reading analysis or something where it was like, this one doesn't let you do that. Okay, so this is like one of the only ones that will never let you do it. So this one's saying put them with the following in the order with the most. So I'm just going to draw you a picture. I'm going to let you figure it out. I don't want to give you the answer outright. Right, I don't want to give it to you outright. But here's the way it works. So you go with, so typically you start out, whoa, I did not pick my pen apparently, or I unpicked my pen. Right? So you have a normal distribution, right? Then remember we said the t distribution is what? What's the t distribution in compared to the normal distribution? What's the word I used?
That's heavier.
It's true. Sometimes it has heavier tails. It's a heavy tail distribution, right? So it's like right? So that would be like a t distribution, and maybe with a small sample size, right? It's heavy-tailed. But what's supposed to happen to the t distribution as what happens to the t distribution as you take more samples? It starts to look more what? Starts to look more normal or bell-shaped. So if I take more samples, it's going to look a lot more like that normal distribution. So that would be t distribution with a large n. Okay, so which one's the heaviest tail distribution?
T distribution is 30 degrees.
So t distributions with small sample size are the heaviest tailed. Which one's the least heavy tailed distribution? A normal distribution. Yeah, a normal distribution is always less heavy tailed than a t. But as you get large sample sizes, then the t distribution gets less heavy tailed. All right? Okay. Oh, that's loud. All right, I like those colors.
Getting
All right. Any other questions about the homework? Yes. Okay, and then Steven, you had a question too?
Yeah, the first question on the second section of 9.
Okay, so
If you
let's
go all the way to the very end. He has the choosing correct procedure.
okay. So let me go here with Marina's because it sounds like yours is long. However, we'll get to number 5. Oh, that's because I haven't showed you how to do the p-value approach. I'm going to do that today. Hold that question on the p-value approach. I'm going to show you how to do that today. Okay, and then Steven, you said on homework 9.
Yeah, it's not a long question, but it's like there's
This one.
yeah,
Number
number
1. Simple random survey 450 individuals who are currently employed, asked if they work at home at least once per week. 450 say they do. Calculated 99% confidence interval for the population proportion of employed individuals who work at home at least once per week. Okay.
It's just like when you're plugging it into the formula.
Uh-huh.
For some reason, every time I get that number, it's just
You know what I think it is, actually, and someone from my online class brought this up. I think it's because if you look at a 90. If you actually look at what they use for their 99% confidence interval, where's that Z table that we have?
Yeah.
Really? Didn't I like open this up like forever ago? Apparently it was waiting on me. If you look at what is the Z value they actually use for, you got your Z table on you by chance that I've handed out with the test or whatever? Do they use 2.575? Oh, they do use 2.575?
Yeah.
Okay. So maybe that's not an issue. Because there is one you have to be careful on. If you look at, because if you look down here, no, that's right. 2.575. Yeah, that should be fine. Okay, well, let's try this one then. So they're saying this is a proportion is what they're doing. So we need to calculate a proportion, and then we need to construct a 99% confidence interval. So for 99% confidence, it should be p hat plus or minus. In this case, we're going to use that 575 for 99% confidence times p hat times 1 minus p hat all over n. That should be what we should be able to use that. I don't know. So let's see. So we need to go calculate the actual sample proportion. So the 450 they did 30. We're working from home. So 30 out of 450 would be our sample proportion. Okay. And that would be, I don't know, what would it be? Any takers? I'm not sure. Number 1, I think.
0.067.
Yeah, and we might want to keep a few more just to be safe. That might be a good strategy. Yeah, so I would say maybe, because it's like 0.06 repeating, isn't it?
Yeah.
Yeah, I mean, you might just want to go, because what do they want us to round it to? That's one thing to think about.
Like 3.
They want 3 decimal places, so I would probably be keeping 4 or 5 in all my calculations, because that's going to make a difference. So I would maybe even go out 5 decimal places when I'm doing this. So for my actual evaluation, I would do 0.6667 plus or minus, and then I would be plugging in that for here. So this would be 0.660, sorry, 6667. The complement of that would be 0.93333 all over 450. So keep as many, just keep as 5 or 6. I mean, as many decimal places as you can comfortably keep. And then let's see what we get for that. So 0.06667 times 0.33333. Divide that by 450. Take a square root. What do you get? Let's see, square root. Multiply that by 2.575. I get, for my margin of error, I get 0.01810.
So you're just multiplying what you get out of there by 2.575?
Yeah.
You're not doing the addition on the outside first?
Oh, no. That could be a problem because order of operations says multiplication comes first. So you need to evaluate this whole thing before you do your plus and minus. Yeah, that would definitely make a difference. Yeah, big time.
Yeah. Okay.
Yeah, so yeah, we got to do all that whole thing first. The plus and minus is the last step.
Probably exactly.
Yeah. So that would make a difference. Yeah. Yeah, and then you go down. So from there, might as well finish it off because we're pretty much there. So that's 0.06667 minus 0.01810. So our lower bound would be 0.04857 up to what would the upper bound be? .08477. So then they want to round to what? 3? So 0.049 up to 0.085 maybe would be our bounds. That's what I'm guessing. Let's see if we get it right. What did I do? Did I round that right? Feasibly, yeah. So let me see what StatCrunch tells me is the answer. So that's another thing I'll do if just to check my answers is I'll let StatCrunch give me an answer and see if we agree. Let's see if I was just off by a decimal place or something. So we're doing stat proportions, and we have summary stats. So we had 30 successes out of 450, and we wanted to do a confidence interval 99%. And oh, what did I do? I don't know what, mine was way off. I must have multiplied wrong. My margin of error must have been wrong. Apparently. Did anybody else do that and get a different margin of error?
Is that asking for your lower bound though?
Yeah, it's asking for your lower bound. So did anybody do this and get a different margin of error? Yeah, I'm thinking I did that wrong. 0.11. I think I calculated. I did use my iPhone. What was it? 0.1176? Something like that. Yeah, because StatCrunch is getting the answer 0.0363. So that was the standard error. Oh, okay. So that's the standard error, but then you had to multiply that by 2.575. Because that would be yeah. So this whole square root thing should come out to 0.01176. I did something wrong in my calculator. Multiply that by 2.575, then that would get you your right margin of error, which would be what? Multiply those together. Something like that. So then add and subtract that. That should be able to get you to these limits. So it looks like the actual answer would be 0.036 up to 0.097. Yeah, I did that. I did my calculation wrong. But regardless, the answer is still yes. You need to multiply that stuff together before you add and subtract it. So that's an issue on top of my issue. But okay. Yeah, I try not to use my iPhone calculator that often when I'm doing math, but nah. All right. Any other questions from the homework? Okay. So for the upcoming exam, where'd my? Oh, I have my. You know what I did? I know what I did. I didn't post them on my math lab. I got them in my email. So hopefully I don't have any sensitive stuff in my email because I'm about to log on to it. So let's see if there's anything good in there. Ed Ori, nope, not that interesting. For me. Dang, I get a lot of emails. Shoot. Okay. That's not me. Well, I've read them all. There we go. That's what I actually want. I want the one that's actually filled in up to where we were yesterday. That's where we were yesterday, yeah? So screw that. That's my old stuff. Okay. So as far as the exam, I'm gonna modify the content just a little bit, just based on where we are. So for exam 4, that's gonna be we're gonna cover 9.1, 9.2, and 9.4. So that was the confidence intervals. Okay, confidence intervals. And then we did confidence intervals both for P and for mu. And initially I was going to get us all the way through chapter 10, but we're just not going to quite make it. So I'm going to cut off chapter 10 at 10.1 and 10.2. And 10.1, 10.2, this was where we're talking about hypothesis tests, but I'm going to cut us off at hypothesis tests, and we're only going to do about the proportion because I don't have time to get into the mean stuff. Only about P, proportions. So we're going to cut it off there. And if you look, I posted a practice exam, and if you look at the practice exam, I don't have hypothesis tests about the mean on the practice exam. They're not on there. And if you compare that to the homework, don't need my email anymore. Oh, what did I just do? Okay, I think we're okay. If you compare that to the homework, that means in the homework, you can stop at about problem, let's see. I'm going to have to extend the homework, but you can stop at, go back. There you go. Stop at problem 14 on the homework. On the very last homework. I'll extend that out past the test, but for practicing for the test, maybe try taking it up to part 14, and then save the rest for after the exam, because that's where the proportion. Yeah, 10.1 and 10.2 will be there. We're just not going to quite make it to 10.3. Yeah.
So the columns that was in it and then extra heading.
No, I'm just going to push the assignment off until next. You'll still have to do the whole assignment. I'm just going to push the whole due date back. So, I mean, technically you don't have to do them before the exam, but it'd be good. You should, for practice. You should do 1 through 14 so you're ready for the exam. But technically they won't be due till after it. Okay? All right. Any questions about that? Right, so there you go. Confidence intervals, proportion and means. Hypothesis tests only about proportions. We're going to cover hypothesis tests about the mean next week, right before Thanksgiving break. We'll get that out of the way. And then there will be just a few little things I'll include the last week of class. But we're almost done, which is good. All right, so we went ahead. So we were developing these strategies for doing a hypothesis test about the proportion. I don't know how many we're going to need here. Right? And so we came up with a strategy that involves basically 4 or 5 steps. First, you state your hypothesis. Then you go get cutoff values. We call those critical values. And those critical values establish a rejection region. Then you calculate the test statistic. It's always the same for proportions. From the test statistic, you see if it's in the rejection region or not. Based on that, you make a decision. You're either going to reject the null hypothesis or not reject the null hypothesis. Okay? And at the end, you're going to interpret it. Say kind of what it means. And yesterday, we kind of got into this. We kind of got into this discussion about, well, why do we say certain things, right? So you can really only make 2 decisions, right? You can either reject the null hypothesis, which means that there is evidence in favor of the alternative, right? That's typically how we phrase it. Or you can fail to reject the null hypothesis, which means we would phrase it as there is not enough evidence. And the wording is kind of weird. It's kind of like, well, why do you phrase it in such a weird way? Why don't you just either say you reject the null or you accept the null hypothesis? And the reason why is it goes back to the type of errors we have. So if there's a type 1 error, we call that our alpha level, right? And our alpha level is known. So if we reject the null hypothesis, then we have a known quantity. We know how likely it is that we created a type 1 error. But we don't say that we accept the null hypothesis. We just say we fail to reject it, because this type 2 error, which your book calls this beta. So you call alpha the probability type 1. They call beta probability type 2. The problem is that this is unknown, and it changes based on your sample size. So if we fail to reject the null hypothesis, we don't actually know how likely it is that we just made a type 2 error. So that's why we only say we fail to reject and there's not enough. That's why our statements are always in favor of it always says something about the alternative. And we just simply say that we fail to reject it rather than saying that we accept it. It's because we don't know how likely it is that we made a type 2 error. We only know how likely it is we made a type 1 error, and type 1 errors can only occur when you reject the null hypothesis. So, anyways, it's sort of a technicality, but it kind of matters. Sort of. All right. It matters if you want to be technical. All right. So, so far this whole strategy we were taking a critical value approach. So there's actually two strategies. There's something called a critical value approach, and that's what we were doing. So based on your alpha level and your alternative, right, you take that to the Z table, you get a cutoff, and you get a rejection region. Right? And then from there, you go and you calculate your test statistic. Okay, right? So that's what we've been doing. And you see if it's in the rejection region or not. So you take your alpha level based on your hypothesis. You either load all the alpha at the top or at the bottom. That gets you a cutoff. Or you split it in half and put it on both tails, depending on your alternative. And then that gives you a cutoff and a rejection region. You get a test statistic. Is it there or not? Boom, reject or don't. Okay. But there is an alternate approach that we can use, which is called a p-value approach. And the p-value approach, it says, don't worry about the critical value. Go straight to the test statistic. Okay. So don't worry about a critical value. Go straight to the test statistic. Then take that test statistic to your table and see how likely that test statistic is. In other words, calculate the probability. This is that. It's basically the probability of seeing your test statistic. That's what we call the p-values. It's basically saying, based on what I saw, if the null hypothesis were true, this is how likely it would have been. It's sort of like a probability. You can almost think of it as like roughly a probability that the null hypothesis is true, right? And if your z statistic is really big, like really far from the average, really far from zero, then your p-value is going to be really small, meaning that, my test statistic was so far away from the claim that this looks really unlikely. If your test statistic is really close, so like maybe you have a really small z-value, then your p-value is going to be really big. So then the way we use it is you compare. You say, does my p-value, is it less than what I was going to allow for my alpha level? And if so, you're going to reject the null hypothesis. Okay? So I'm going to give you an example. We're going to do it both ways. I'm going to show you the critical value way. I'm going to show you the p-value way. And then we can decide which one is easier. They're really, neither one's easier than the other. Okay? So it's just two different approaches. But as long as you do it right, they better give you the same result. If they don't give you the same result, then you got problems. You did one of them wrong. All right. So let's do an example. We'll go both approaches. We should be getting pretty good at the critical value approach at this point. Okay, so let's say it's known historically that 1.9% of patients that take cholesterol medicine have side effects. I don't know how to spell cholesterol. Let's say they have flu-like side effects. What's that? Patients. It's supposed to say patients. I missed some letters, and the other ones didn't look like letters. So, but 1.9% of patients taking cholesterol meds, they have flu-like side effects. So, so then another drug comes on the market. It's a pretty popular one. It's called Lipitor. So let's say there was a study done, and a study of 863 Lipitor patients. So these are people taking Lipitor patients. It showed that 19 had flu-like side effects. So what percent of the Lipitor patients had side effects? What's our sample proportion here? 19 out of 863. What is that? Somebody got that? 0.022. So in our study, like 2.2% of patients taking Lipitor had flu-like side effects. So what might you think could be true about Lipitor potentially based on our sample? It looks like maybe Lipitor is what? Compared to other brands of cholesterol medicines? It's what? Yeah, so it looks like it's potentially Lipitor might have higher side effect rates, basically, or they might have more people have flu-like side effects, so it's going to be worse in that term. So that's what I want to test. So let's test at the 0.01 level. At the 0.01 level, test if Lipitor has higher rates of side effects. All right. Okay. So with that in mind, what's our null and alternative hypothesis? So our null hypothesis is that Lipitor is just like every other drug. It's going to have a 1.9% flu-like side effect rate. And we'll just assume that until we can prove otherwise. What do we think could be the case, though? Yeah, we might think maybe the true proportion for Lipitor is actually higher than that. All right? All right. So now what do we need to do? If we're going to do a critical value approach, we need to go find a what? Close. There's one in between. Yep, we need to go get a critical value and establish our rejection region. So our alternative is greater than, so what are we going to do with all our alpha level? Yep, we're going to pile it all up in the top tail. So we need to go get the cutoff. We need to go find z sub 0.01. So you go to your table, you look up z sub 0.01, and what do you get? Let's see. You guys might already have it. I think I got it somewhere. Z sub 0.01, so that's the 99th percentile. And so it looks like that's going to happen up around, looks like here. So 2.33 is going to be our cutoff. So that's our cutoff, and then everything above 2.33, that's going to be our rejection region. Okay. So we know the test we're going to make, or we know the test we're doing, we know the cutoff, and we know where our rejection region is, so now what do we got to do? Now we get the test statistic. Yep. Okay. So now we're going to go get our test statistic. So our test statistic, it's always that we're doing proportions. So it's just going to be this value. Okay. So our p hat, what was our p hat? Was it 0.022? So that was our p hat. Is it like 2-2 repeating or something like that?
220.
Okay, cool. And then minus the null hypothesis all over, that's going to be 0.019. 1 minus that would be 0.991. No, 981. All over, our sample size was 863. All right, so go ahead and find that that z-score. Tell me what you get. Round it 2 places and tell me what it is approximately. We'll see if we can get some agreement. So you do the square root in the bottom and then divide that into whatever 0.022 minus 0.019 is. What's your z-score? Dude. It's back. I want to check something actually. So while you're doing that, I want to check my fountain. It says it's still going. Okay. So you got what?
0.645.
So 0.65 or 0.65? 0.65? I got another one for that. 0.65. So that's our test statistic. Does this seem like a particularly strange outcome based if the claim really is 1.9%? Is that a really extreme test statistic? Right, because remember, where is our rejection region? Our rejection region is up at what? It was way up here at 2.33. And where is our test statistic? It's way down here. So, should we reject the null hypothesis or not reject the null hypothesis? Remember, the rejection region is...
Not reject for 1,000 hours.
Okay. So, I think if it was up here, we reject. But where's our test statistic? Down here. So what should we do? Don't reject, yeah. So, we're going to fail to reject the null hypothesis, which means essentially there is not enough evidence to support the alternative. Right? So we fail to reject the null hypothesis, meaning we can't support the alternative. So as an interpretation, what are we actually saying about Lipitor? Are we saying it looks like it does have higher rates of flu-like symptoms, or are we saying, as far as we can tell, it looks like it's just like every other drug? The second one. What I just said. That's right. So we failed to reject the null hypothesis. We couldn't prove our alternative. So we're basically saying, as far as we can tell, it looks like the null hypothesis is true. So it looks like Lipitor, as far as we know. So I'll just say that. As far as we can tell, Lipitor is not any different in terms of side effects. So, looks like it's basically the same. As far as we can tell, is it possible? Maybe it is a little worse than other drugs. It's possible. But based on our sample, we don't have enough evidence to come out and say that for sure. Okay. You would probably have to maybe take more. If you really, really believed it, you would want to go take another sample or a larger sample to try to get that, to try to maybe make that claim. Okay. Now, that's the critical value approach. But in the p-value approach, we take a little bit different. We take a little bit different strategy. So in the p-value approach to this test, okay, we still have the same. We're still doing the same test here. Okay, alpha 0.01. But in a p-value approach, you go straight to the test statistic. Okay. So in the p-value approach, we're going to go straight to that value we calculated. Which actually we already know what it was, right? It was 0.65. We already calculated that in the last one, but you should be able to get the same answer if you do it again. Right? So in the p-value approach, you say, okay, now what I'm going to do is I'm going to take that test statistic to the z-table, and I'm going to get a p-value from the table. So you go to the z-table, and you're going to look up your test statistic. And your p-value, since our alternative is greater than I shouldn't underline that, looks like greater than or equal to now. Since our alternative was greater than, right here, our p-value is going to be whatever probability is greater than our test statistic. So we're going to go to the z-table and look up 0.65 on the table. So 0.601234 So 0.7422, that's below, right? So 0.742, did I get that right? So this is 0.7422. Maybe, there we go. And so that means above would have to be what?
0.2578.
0.2578. And this is our p-value. So our p-value in this case is 25%, almost 26%. And the way we can interpret our p-values is we can basically, you can almost think of it as like there's like a 0.2578 chance that H naught is true, sort of. That's sort of how you can interpret it. So based on what we saw, there's still a 25% chance that the null hypothesis is true, sort of. But what we do is we make our decision by comparing it to our alpha level. So we say, okay, our p-value was 0.2578. Our alpha level was 0.01. Which one's bigger? Our p-value is way bigger, right?
Yeah.
So our p-value exceeds our alpha level. And so we would fail to reject the null hypothesis. So we would come to the same decision as we did in the last one. We don't really need a critical value. We just need our p-value. And we compare that p-value to the alpha level. So if your p-value is big, don't reject. It's saying, hey, it looks like, if your p-value is big, you're essentially saying, hey, it looks like the null hypothesis is pretty reasonable. But if your p-value is really low, that's saying this null hypothesis is looking very unlikely. All right. So the general rule to the p-value approach is, right, if your p-value is less than alpha, reject. And if your p-value exceeds alpha, fail to reject. Okay. One of my students one time, he said, this is the way you remember. So he said, if p is low, null must go. Okay, there you go. So low p-values mean reject. All right? Think you can remember that? P-value low, null must go. Reject. All right. But notice we came up with the exact same decision. All right. So if you're gonna do a one-sided test, like a greater than or less than alternative, either one of these is perfectly reasonable. It's really up to you how you want to report it. But typically, I think more in practice, we use a p-value approach because what they'll do is you can report the p-value along with your decision. You say, I made this decision and the p-value was, this. And so that gives us a better idea of, you know, how strong was the evidence for or against the null hypothesis, right? Okay, so yeah, I think that's which one? This one?
That
Yeah. So two different approaches, same result. I think typically I would use typically I would do a p-value approach, I think. StatCrunch will calculate p-values for you if you do those hypothesis test options. I'll show you how to do that in a second. Because there is one other thing I wanted to mention too, though, is that, you know, this idea, where are we at? I want to go back to here. You know, it's pretty clear when your alternatives are, you know, right-handed or left-handed alternatives. You just load all your alpha up on the top or load all your alpha up on the bottom. That gets your critical value. Or your p-value is just everything above or everything below your test statistic. The two-sided alternative is kind of annoying because you have to do it differently. But there's actually a shortcut you can use on two-sided tests. So if you have what they call a two-tailed or a two-sided test, you can actually just do it instead with a confidence interval. And I'll show you how that works. So I'll give you an example. Let's say, so in 1994, 52% of parents, they thought that kids weren't getting taught enough math in school. Math in school. So they decided to see if attitudes have changed. So in a recent survey of 800 parents, 256 felt the same way. So my question is, at the, say, 0.05 level, is there evidence that opinions have changed? All right. So what's the null and alternative hypothesis? So the null hypothesis would be that what? Yeah, we're going to say, we'll just assume that attitudes haven't changed at all. We're thinking maybe we can show what? They have changed. So, but we're not really stating up front which way, so this would be a not equal to alternative. Just have they changed? They might have gone up or down, we don't know. Now, if we were going to actually do this test the way we were doing before, what would we need to do to get our critical values? What would we have to do with that alpha level? We'd have to divide it in half, put half of it up here and put half of it up there. And then our cutoffs would be 1.9. You could get it from the table. 1.96 and negative 1.96, right? And then our rejection regions would be out here. Yeah? Okay. And then if we did our test, so then we would go get our test statistic. So what is our p hat here? Yeah, so it's 256 out of 800, and that comes out to be what? 0.32. Looks like it's dropped. It looks like the percentage of parents has dropped. Okay, so that's our p hat. So then we could go get our z statistic. So our z would be 0.32 minus the null all over, p naught times 1 minus p naught all over 800. Right? It's that p hat minus p0. So our p hat's 32%, p0 is 52%, all over square root of p0 times 1 minus p0 over n. And what do you get for that z statistic? It's probably going to be pretty big. I don't know. I would think. What is it? It could be right. Yeah, it could be really big. Negative 11.1. That's, yeah, I mean, that's weird, but it's not necessarily unreasonable. Did anybody else get a really big one? Negative 11 point something. What else do you guys get? It sounds like it's negative 11 something.
I got a negative 11.322.
Okay, something like that.
Yeah.
Okay, so this is, right? Remember where our cutoffs were? Where is negative 11 point something? It's like way over here off the page, right? So negative 11.32. It's way down there. So is it in the rejection region?
Yeah.
Big time. It's way out there in the rejection region. So what should we do? We should definitely reject, right? Which means that there is evidence that the percent is different than 1994. It looks like it's gone way down. It looks like parents' concern about how much math they're learning has gone down for whatever reason. So there's definitely evidence that the percent is different. It looks like our alternative was true. It's changed. So that would be the old way to do it, or that would be the way we were used to doing it before. But notice our cutoffs. Our cutoffs are exactly the same values we would have used for a 95% confidence interval, right? So the alternate approach would be, well, let's just calculate a 95% confidence interval and see if the claim is contained in it. So we're going to calculate a 95% confidence interval and see what it looks like based on our sample. So in our sample, it was, our p-hat was 32%, plus or minus 1.96, 0.32 times 0.68, all over. How many adults was it? 800. 800. Okay? So what do you get? Multiply those decimals, do the square root times 1.96, and let's see. I got 0.0323. 0.0323,
Yeah.
right? So then that would say our interval would go, so subtract it, that would go down to what, 0.2, would that be 0.29 or would it be 0.28 something? Will you do that for me? Do the subtraction and the addition. So 32% minus, I think it's going to be 0.2877. Is that right? Up to 0.3523. 23. Yeah. So notice that whereas this is saying that we're 95% confident that the true proportion is somewhere in this range, right? But if you look at it on the number line, our P0 was 0.52, and our interval is entirely down here, right? Our confidence interval is way down here at these lower percentages. The claim is way up at 52%. Does 52% seem like it could reasonably be true based on our confidence interval? Not really, because our confidence interval doesn't contain that. It's not anywhere close to that. So based on our sample, We think the truth is somewhere down here between like 28 and 35%. They're trying to claim, the claim was that the truth is still 52%, which just seems totally unreasonable. And so the way you do this is you say, okay, so P naught is not in our confidence interval, so then we should reject the null hypothesis. So you calculate the confidence interval, and you say, hey, does this confidence interval claim even contain that claimed value? And if it does, then you say, okay, seems reasonable. I believe it. If it doesn't, though, say, nope, that doesn't seem reasonable. Let's reject it. Okay. So that's the that's only, though, you can only do that with a two-tailed test. You can only do it with a two-tailed test. Because if you try to do it with a not two-tailed test, well, it just won't work, so don't do it. You won't have the confidence you think you have. You'll have the wrong alpha level. You'll think you'll have one alpha level, and you'll actually have a different alpha level. So you'll think your alpha level is 5%, and it'll actually be 10%. So yeah, I think that should get you through what you need. So with the homework, do the homework like we were talking about. Practice test is posted. Practice test is there. And then come tomorrow with lots of questions, and we'll answer them. All right?